Hello, everybody. Welcome back to CSE 373. Today, we're going to continue our discussion of minimum spanning tree, but we're going to focus on a different algorithm and a new ADT and some implementations of that ADT to help actually run it. Notice I'm looking a little bit fancier today in terms of where my webcam is placed, just because this slide deck has lots of animations and pictures. So I want to make sure I'm really out of the way as much as possible. So before we begin, I want to start with some announcements and then doing a bit of review before jumping into this new algorithm. So Project 3 is due Wednesday, which is the day of this lecture, at 11:59 PST like normal. That day, we're also going to be releasing our last project. So Project 4 is the last project of the quarter, and it's going to be released the same day. If you haven't already, you should have received an email about the Project 4 partner form. So if you're looking for us to match you with a partner, please fill that out before Wednesday so that we could release partner assignments. In terms of what we're trying to learn today, we want you to be able to describe, compare and contrast, and implement kind of the things that go behind the scenes for this new algorithm we're going to talk about called Kruskals Algorithm. So we're going to introduce kind of in this video what the algorithm is, and kind of how it works in theory. And then in the later videos, we'll talk about a new ADT and data structures that will help us implement this. So as a bit of review, last time we introduced the idea of a minimum spanning tree. The problem we were trying to solve was connecting a bunch of cities to the power company such that all of the connections that we chose to use had a minimum cost. And so we framed this problem as a minimum spanning tree problem, finding a tree, a set of the edges that span the graph, that connect all of the vertices, such that all of the edges we choose have a total minimum cost. There are many spanning trees on any particular graph, potentially, but there's we're trying to find the one that has minimum weight. And so we wanted to highlight, some key properties about this minimum spanning tree. When we have this minimum spanning tree, it does not necessarily minimize the path from each vertex to every other vertex. So for example, the path from F to D is pretty long, right? You go F is 6, F to B is 6, B to 3, or B to A is 3, and then A to D is 4. So that's a total of like 13. So it is not shorter than just taking a direct path from F to an 8. But the idea here is being that we can connect the whole graph, and this subset of the edges has a minimum cost. It gets everything connected with the lowest cost, but it does not guarantee anything about shortest paths. If you have a tree graph with V edges, then a tree that connects them all will have, V vertices. A graph that will connect them all will have V minus 1 edges. And do note that this is kind of a separate entity from the graph itself. Like, we still have this underlying graph with all of those edges. We're kind of choosing a subset of the edges to highlight or annotate as kind of this minimum spanning tree, kind of like that shortest path tree that we did with Dijkstra's. So that's kind of the context. And we kind of highlighted that minimum spanning tree algorithms that help you find minimum spanning trees, they generally work because of one of two properties. First, the cycle property, saying that if you ever have a cycle in your graph, then the heaviest edge on that cycle will never be part of a minimum spanning tree, because you can connect all of the nodes in that cycle using all the other edges. That kind of one extra edge to complete the cycle is unnecessary. It's extra cost, but doesn't get you any extra connection. And we also talked about the cut property, which is a little bit more complex, which is, as a reminder, a cut is any partition of your nodes. So separating the nodes into two sets. The cut property says that if for any cut, in some sense this has to be true for every possible cut, then there's going to be an edge that has to cross the cut, and we're always going to choose the one with minimum weight. So if an MST exists, then it will choose the edge with minimum weight that crosses any cut of the graph. So always choose the lightest edge, the one with the the smallest. And this is kind of the key idea behind Prim's algorithm. Prim's algorithm had that known set and everything else. And we were saying that we would always include the edge with minimum weight that crosses that cut. And that's why we always choose the next closest edge. Now, a couple things that we'll talk about kind of later on is this idea that these algorithms are what we call greedy algorithms. What I mean by that is that they kind of make a locally optimal choice without having to consider everything possible in the graph. So like with prims, we always grab the edge with smallest weight and add that to our minimum spanning tree. We never undo a choice. And so we call these type of algorithms that are kind of iteratively adding to a solution without having to go back and revise anything. We call those greedy algorithms. And those are kind of in opposition of brute force algorithms that would maybe try every possible tree and then see which one is the minimum spanning tree. If we tried that, we'd have to enumerate all possible spanning trees, which is what we'd call a brute force algorithm. But a greedy algorithm is usually clever and it can sometimes work in the sense that you build it up iteratively and you're choosing like the locally optimal thing. And if a greedy algorithm works for your problem, that's great because then you can solve the whole problem without having to enumerate all possible. So the algorithms we talked about on Monday, are this type of greedy algorithm. So what we did to talk about Prim's algorithm was we adapted Dijkstra's. So remember with Dijkstra's, we had the known set and the unknown set, and we were keeping track of path lengths from the start vertex. Prim's is similar but different. It operates a lot in the same ways, but we don't care about path length. We don't care about the length of an entire path from a start vertex. So instead, we define distance to a node as just the edge weight to get to that node from the closest node in the known set. So this is kind of going back to that cut property. We defined a cut with everything we've known so far and everything we don't. And we always choose the edge with minimum weight to cross this cut because any other edge would incur extra cost. So Prim's algorithm worked a lot like Dijkstra's, but we changed this distance to only work with just the edge weight W. Choose the one with the smallest. Now, what I want to highlight is we could potentially take a different approach. So suppose I ran Prim's algorithm on this graph and it produced this MST. You might notice that all of the edges it chose tended to be the smaller edges. And that kind of makes sense because it's supposed to be a minimum spanning tree to hopefully find us edges that are small. So if you kind of look at all the edges it chose 1, 2, 3, 4, 6. And so you might be wondering, is this a more general pattern? Can we just choose the smallest edges in the graph and call that a day? It's not going to quite work like that, but an idea similar to that will end up working. So the one exception to one edge that wasn't chosen in part of this minimum spanning tree was 5. Why didn't we include this edge 5 here? If I draw this here, why didn't we include this edge in our minimum spanning tree, even though 5 is less than the 6? Well, that's because including 5 makes a cycle. Remember that our minimum spanning trees are trees. They can't have cycles. So we wouldn't want to include the 1, 4, and 5 because that adds a cycle to our graph. So that kind of gives us an idea for how to go about building up these minimum spanning trees. Start by adding all of the smallest edges, but never choose an edge that would cause you to make a cycle. So kind of start by picking the edge with 1 and then 3 or 2, 3, 4, but don't include 5 because it has a cycle. And that idea is kind of what's behind this other algorithm called Kruskals Algorithm. Prim's algorithm kind of operates vertex by vertex. You kind of start at some source vertex and you kind of iterate outwards, always finding kind of another vertex to add to your minimum spanning tree so far. But here we're going to start thinking more about edge by edge, trying to find the smallest edge in the whole graph and including that. So we always are going to add edges to our minimum spanning tree as long as it doesn't create a cycle. So Kind of what I highlighted here was this kind of edge by edge approach is you start by adding edge 1 and then edge 2, 3, 4, but skip 5 because it creates a cycle, and then 6, and then we know when we're done when we've added v minus 1 edges, right? Remember, a tree that spans the graph of v vertices will have v minus 1 edges. Once we've added v minus 1 edges, then we're done. Now, what we need to be able to answer for this kind of algorithm is how to do this and how to detect if an edge would create a cycle. So that is where we enter Kruskals algorithm. Build MST edge by edge, starting with the smallest edges and going to the largest. The key intuition of Kruskals is that we're going to kind of consider having a bunch of separated islands. Each island is a set of nodes that have currently been connected by the MST we're building up. They're kind of like sub MSTs. Now, we're going to start with each vertex in its own island. So we're going to start with V islands in our kind of graph. They're all separated. None of them are connected. Then what we're going to do is we're going to iterate through the edges, starting at the smallest edges in the graph to the largest. And if we ever find an edge that connects two islands, we're going to include it in our MST. If the edge is already is between nodes that are already in the same island, we're not going to include it because that kind of island is already kind of. The idea is that we're kind of having separate connected components. Each island is a set of nodes that we already have connections for. They're all connected by themselves, and now we're joining these islands together. So I'll walk through an example of how this runs in a second, but I kind of want to briefly mention the pseudocode behind this. So we're going to need some kind of structure, something like a set, to store all of these sub minimum spanning trees. And then we'll probably have like a set of edges for the final minimum spanning tree. And we start by making everything in its own island, its own kind of sub MS. Then we start by sorting all of the edges by edge weight, and we just iterate over all of the edges. So we start at the smallest, and we say, okay, well, look at the two nodes that are on either side of this edge. Are they part of the same island? We're going to want some kind of structure that can tell us what island or what subset is this node part of. So we need something to kind of manage these subsets. And so we'll just call this having some find operation, find which subset this node belongs into. And if they're in different subsets, then combine them. So add that edge to our minimum spanning tree and somehow use some kind of union operation to union those sets together. Now, how to do find and union? I haven't explained that yet. We're just going to want some type of data structure that's able to do that. So here's how this is going to go. We start off having everything in its own island. Then we just start with the smallest edge, which is 1. 1 connects A and C. Those are in different islands. So if we do this find operation, it's going to tell us which island it's in. We see that they're different islands. So we're going to add that edge to our MST and union those two islands together. So we've added this edge with weight 1, and now we've combined those two islands. And now we repeat. Go find the next smallest edge. That's 2, this edge 2 here. That connects B and F. Since those are in different islands, we add it to our MST, and then union those two islands together. And we just repeat this over and over again. Next smallest edge is 3. Those were in different islands, so we union them together and add that edge to our MST. Same with 4. Those were 2 different islands before. That 4 crosses those islands, so we add it to our MST and then union those sets together. Now we get to 5. However, 5 we're not going to add to our MST. How do we know this? Well, it's the two nodes that it connects, E and D, they're part of the same island right now. So if you had this kind of structure that was able to tell you efficiently which island is a particular node in, this would say, oh, they're both part of the same island. So we don't want to include this edge in our MST. If they're already connected, then adding another edge will form a cycle. So if you have kind of in this subset of nodes, A, B, C, D, F, we don't have any connection to E yet, so ignore E. But if we have this subset of nodes and we currently have a minimum spanning tree over this subset of nodes, then adding any edge will have to form a cycle. And that cycle is not what we want in a tree. It's only going to increase the cost of our solution, doesn't buy us any connectedness. This kind of island is already connected. And so we don't want to add this edge. And so we skip. We skip the 5, go to the 6, and see that's 2 connected components. And then at this point, we can stop because we've now built up this minimum spanning tree to have v-1 edges in it. So I want to quickly show you kind of a visual intuition for how this works. So I showed you these 2 videos last time. These 2 videos show you prims and Dijkstra's. And we talked about for prims, it's kind of adding edges to expand this cloud of known vertices. And it's building up this MST iteratively, kind of going vertex by vertex. And we saw that there's this kind of interesting behavior where prims kind of treats the nodes it's adding, doesn't consider the whole path length. So it's going to actually kind of maybe go off and explore for a long time, while Dijkstra's is really going out, kind of in concentric circles-ish. Again, the path distances control what you explore next, but prims kind of has this ability to kind of go out into the graph because it's not considering whole path lengths. Well, Kruskals is going to end up looking a little bit different. So if you consider how Kruskals is going to work, since we're always adding the smallest edge in the entire graph, we're going to kind of have all of these disjoint trees. So each one of these kind of subtrees, these sub-MSTs, are kind of like, for this little island of stuff, what's the current best MST? And we're always adding edges to combine 2 of these sub-MSTs. And so the way it builds up this minimum spanning tree is very, very different. However, they're both trying to solve the same problem. They're both trying to find the minimum spanning tree. Prims just does this vertex by vertex, while Kruskals does this edge by edge, noticing that we're going to include the smallest edges as long as they don't form a cycle. And that's why we have this check to make sure we don't add a small edge that would cause us to have a cycle. So in the next video, what I want us to talk about is how to actually implement this stuff. Like, I talked about this ability to find what island a particular node is in and being able to union 2 islands together. How are we actually going to do that? And what data structures will we use? That's kind of the topic for the rest of the lectures, or the rest